I think there are just a couple small places where my notation is likely to stay different just because that's how it's organized in my head. So let me just be clear that I'll tend to denote the edge weights by TE. Instead of tau E. And I'm going to use, so this capital T for the metric, I'm going to use in every case. So instead of having separate symbols T and L for the metric and for the passage time along fixed paths, I'll denote them both by T. So just to remind you what we spent the end of the first lecture, we spent a lot of time on, also to fix the notation again. So the kind of fundamental first theorem that you need to know is the shape theorem, which says that under a moment assumption, and also under the assumption that you have a smaller than critical fraction of zero weights, F0 less than QC, there exists some limit shape I'll write as calligraphic B, such that for all positive numbers epsilon, the probability that the random set E of t is sandwiched between a slightly shrunken down copy of the limit shape and a slightly blown up copy of the limit shape for all large T is 1. And indeed, there was this alternate characterization given. So just to restate that, we can write the limit shape B as the set of all x such that mu of x is less than or equal to 1, where mu, so it was defined slightly differently in the lecture, but a way to define it without invoking the subadditive ergodic theorem is mu of x is the limit as n goes to infinity of the expectation of the passage time to nx divided by n. And this limit exists by subadditivity, this Feketa's lemma for subadditive sequences of real numbers. And these properties were also stated, I think you'll prove them as an exercise in the tutorial, but so one way of summarizing part of the properties of mu is to say that mu is a norm. So that follows from properties of the model. So this characterization says that the limit shape is the unit ball of this norm mu. Okay, so none of that's new at this point. This is just a reminder. When you have, a theorem like this, I suppose the next natural thing to ask is, what can you say about the limit shape? So what are the properties? Of B? Of course, you probably expect the properties to depend on the choice of distribution, but as we'll see, a lot of things that are believed about the limit shape should be kind of roughly independent of the choice of distribution, as long as it's particularly nice. So, right, what is known about the limit shape? Well, The bad news, or perhaps good news, depending on your point of view, is not much in general. So the most interesting questions about the limit shape are still open and have been open for a very long time. As we saw last time, of course, we know that this limit shape is convex, meaning if I take 2 points in the limit shape, then the straight line segment between them is also contained in the limit shape. It's compact. And it has non-empty interior. Another thing which has been kind of implicit in things that have been said so far, but is worth making explicit and is also related to a problem in the tutorial, is that the limit shape has the symmetries of ZD, which fix the origin. So this follows from the symmetries of the model, just to make it hopefully explicit enough for anyone who is not convinced. For instance, mu in the E1 direction is the same as mu in the E2 direction because the distribution of the metric t is invariant under change of coordinates. Okay, so I think it's fair to say that this is about everything that we know in generality about the limit shape. What do we expect and what do we want to know? I'll call these conjectured properties. And I'll say, again, this is perhaps for nice distribution functions f, for nice to be determined. What exactly niceness means is kind of part of the problem as well. These are believed based on simulations. They're based also on some other models where you can actually show things like this, and also some physics arguments, which also seem pretty far from any kind of careful mathematical argument. So first, E should be strictly convex. So to be clear, if I take two distinct points, x and y, in the limit shape, and I take some number t strictly between 0 and 1, then I believe that tx plus 1 minus ty is in the interior of the limit shape. Or in other words, that the norm of this point is strictly smaller than 1. So that, that is true. For instance, just thinking about this as a property of general convex sets. That's true for something that looks like the Euclidean ball, a line segment between 2 points, except for its endpoints lies strictly in the interior of the ball. It's not true for something like a diamond, the L1 unit ball, where if I take 2 points on this side, then the entire line segment between them also lies on the side, and so not in the interior. So as I said, this is conjectural. It's not known for any choice of distribution. There is a theorem from a little while ago by Steve Lowley, where he showed that strict convexity would follow from two, I think it's fair to say, very strong assumptions. So he gave an argument, conditional on these two strong assumptions, which also themselves seem very far from proof. And one of them, it's not really clear that it should be true for the model, actually. So, so this is a difficult question. Okay, good. So also the boundary of B should be differentiable everywhere. In other words, at each vertex X in the boundary, there should exist a unique supporting hyperplane H sub X having the property that X is in H sub X, but the whole limit shape lies on one side of H sub X. So again, the Euclidean ball is differentiable. The L1 ball is not differentiable. It's kind of misleading to take the same example for both of these because these are different properties, but yeah, hopefully that illustrates it. Any questions so far? Yeah.
There's an example that with non-degenerate distribution where B is not strictly convex.
Yeah.
Right. Are there examples of where you don't have a differential boundary? Obviously, if you have a degenerate distribution, then you get the diamond. But other than that,
yeah, where you don't have a differentiable boundary. In the IAD case, yeah, other than the diamond, I don't think so. Yeah, maybe someone else, yeah, is aware of an example, but I don't think so. Yeah, okay, good. Oh, yeah. Yeah, so they should probably be continuous. Also, they should have enough moments. How many moments, I don't think is totally clear, but so a lot of the stuff that's conjectured, I think is only supposed to be true under, some moment assumption, because when you have few moments, then the landscape is supposed to look different. And there is some work on at least like last passage percolation where you have few moments, and then the fluctuations and everything I think look a little different because things are dominated by kind of extreme behavior in local places. But yeah, I do think also trying to figure out exactly what conditions might be part of the problem. Yeah. Okay. So good. That's another conjectured property. Even more then item 1, the boundary of the limit shape should have uniform positive curvature. So in other words, there have been a couple, a couple ways that this has been stated. But for instance, if I take also the assumption that the limit shape has differentiable boundary, then there should exist constants C1, C2, and epsilon positive, such that let me write the expression. Right, the way I defined HX actually is slightly slightly bad for the way I want to say this. So if I take X in the boundary of the limit shape, and now I perturb it by some vector Z. So I want Z to actually lie in the shifted version of HX where I shift to 0. So it's really, I'm really just moving in the perpendicular direction. Or not perpendicular, but in the, I'm moving within the supporting hyperplane. So X plus Z looks like this here. Then as long as Z has norm smaller than epsilon, then mu of X plus Z should grow quadratically in the norm of Z. Oh yeah, thank you, sorry. Yeah, thank you. Yeah, right. So this is, this is giving a quantitative version of saying how the limit shape is bending away from this supporting hyperplane at X. Yeah, so all three of these have been used in different arguments. If you were able to establish any of these for any distribution, then you would also be able to prove other things about the model that are interesting in their own right. So each of these would have useful consequences that we'll hear about in the other mini courses. Okay, so these are three properties that we believe should be true. One thing that already came up in a question to some extent that I want to expand on is that there is a class of distributions for which strict convexity is known not to hold. So yeah, kind of interestingly, there's a pretty good characterization, at least of this particular class of what's going on to make them not strictly convex. And so this gives you some idea of yeah, like the kinds of conditions that you would want at least to have that be true. So as we already said, if the TEs are identically equal to 1, then the limit shape B is just the L1 unit ball, which I'll denote by D for diamond. So then the model just becomes, so the passage time now is just the L1 metric, and at least on CD. And so the limit shape is trivially just the L1 unit ball. So in this case, of course, we see there's no strict convexity. Indeed, there's no differentiability because you have corners. Right, so it turns out that for perturbations, of this case, you still have aspects of this behavior. So the limit shape B still looks partially in places like this diamond D. So to describe, what exactly I mean by perturbations, and then, what I mean by looks like D in places, let me give a little more notation, and we'll restrict to the case D equals 2. So we already saw PC for Bernoulli percolation introduced in the last lecture. I want to introduce a related object I'll denote by PC vector. This is the critical probability for oriented percolation. So in oriented percolation, you have edges of Z2 IID chosen to be open with probability P or closed with probability 1 minus P. And instead of studying infinite connected components of open edges, we study kind of infinite connected oriented components. So we study whether there exist infinite open paths that move up and to the right. So following only edges in these two orientations. And PC vector is defined analogously to PC for Bernoulli percolation. So if P is bigger than PC vector, then there exist such components. And if P is smaller than PC vector, there do not. It's a number, yeah. Somehow, at least some people use this notation. Yeah, I agree it's slightly distasteful, but that's, I think, what we've inherited. So, yeah, okay. Right, so for each P, let me define MP to be a class of distributions. So MP is the set of all distribution functions F on the edges such that all edges take value at least 1 with probability 1. And all edges take the value 1 with probability P. So there's a function I'll denote by alpha of P. This is called the asymptotic speed of oriented percolation. if you want to read about this, I really don't want to define it. So if you want to read about this, you can see Duret's review paper from '84 on oriented percolation. This object measures kind of how rapidly these infinite open oriented paths spread out in space as you move forward. With alpha of p is positive if p is bigger than pc vector, and it's 0 if p is less than or equal to pc vector. And this object is going to appear in the characterization of these limit shapes. So let me define 2 points. Let me try to make my notation consistent. So I'll denote them by RP and SP in terms of these values of alpha p, which are implicit. SP is the same thing but reflected. Oh. Maybe I'll go over here so I don't get too far from my statements. Okay, so it's a theorem due to Red and Liggett, and also to Marchand in, I guess, the 80s and the 2000s, respectively, which tells you something about the relationship of the limit shape in the case of this class MP to the diamond. Let F be an element of this class MP. Then, first of all, the limit shape is strictly contained, or not strictly, the limit shape is contained in the diamond. This part is kind of trivial in some sense, because all the edges take weight at least 1. And so to get between any 2 vertices, you have to pay at least the L1 distance and cost. So you can't expect to have your region B grow any faster than this diamond. So the real content is in the other parts. So first, if P is smaller than PC vector, then actually we have strict containment. So the limit shape is contained in the interior of the diamond. You really have to move more slowly. If P is bigger than PC vector, then the limit shape boundary intersects the diamond boundary in the first quadrant, exactly in the straight line segment between RP and SP. So in the first quadrant, my diamond looks like this. My limit shape B, presumably we'll see in a second, but the limit shape bends away from the diamond except on this segment RP and SP. So I'll state the fourth part. Oh no, yeah, that's right. Yeah, so it does indeed bend away from the diamond, except on that line segment. And the fourth part, if P is PC vector, then this intersection from the previous item is exactly the point on the 45-degree line, 1/2, 1/2. Did I start at 10:50? Did I start a little late? 55, okay. Yeah, that's good. Just want to make sure I'm not going way behind. Okay, so yeah, this tells you do indeed have a flat piece for elements of this class and gives you a characterization of what the flat piece looks like that's implicit. Maybe I'll move back here just so I can have a little more space to work. Yeah, this theorem takes a decent amount of work to prove, but if you just want to see that you should have some connection to this flat piece, you can note, as we already said, that any upright path with TE equals 1 for all E in the path is a geodesic between its endpoints. And so as long as you have infinite oriented paths where every edge has weight 1, then you really can move asymptotically like the L1 norm. So all you have to do to see, some tiny piece of this phenomenon that I outlined over here is to show essentially the PC vector is strictly smaller than 1. And that's not so hard to do. So if you can show that PC vector is strictly smaller than 1, i.e. that you have infinite oriented paths with weight 1 for P large but less than 1, then you see that asymptotically you can move at least somewhere at the same speed as for the L1 metric. And this, I don't think it's planned as an exercise for the tutorial, but maybe we can try to include it as an exercise because it's a nice exercise at this level. Okay. Yeah. So, yeah, so if you have an oriented path with weight 1, where every edge on it has weight 1, then that's trivially a geodesic because it has the minimum possible number of edges and all of them are weight 1. If you have a non-oriented path of weight 1, maybe it it's kind of space filling or something almost. And then it has a gigantic weight, you know. You can construct configurations where, like, you know, this edge is weight 2, and then there's some weight 1 path that comes out here and does all kinds of crazy stuff. And the geodesic's just going to be this weight 2 edge. Yeah, this is an important question. So thank you for asking. Yeah, what you're asking, I think, is basically like this asymptotic speed question. So the asymptotic speed, you know, really, so here's your first quadrant. The asymptotic speed is telling you that you have infinite oriented open paths in a cone that sometimes gets called the percolation cone, and the width of it is defined by this asymptotic speed. So I think it's asymptotic speed is half the width of this cone. So yeah, that's kind of, it sounds like the question you're asking really is equivalent to, you know, is a direction kind of outside or inside of the percolation cone? Yeah, that's also a good question. Yeah, there exists, yeah, somewhere exists an infinite oriented path that has a direction in the cone. Yeah, they're pretty wide, and then nothing outside of the cone. Yeah, and you know, you can say a little bit about the width of the cone, but nothing very explicit. You can get like bounds on the width of the cone. Oh yeah. So that's kind of PC vector is less than 1. Yeah, I can kind of so I kind of hastily was cutting the exercise a little bit here, which might be why it seems like this thought is half formed. But why don't I say a little bit more and cut something else, because this is also pretty important. So if you consider a cluster, let me call it kind of calligraphic C of X, such that there exists an oriented 1 path from the origin to X. So this is the oriented version of the open clusters from unoriented Bernoulli percolation. So if I want to control the probability that there's not an infinite set of such vertices so that I can't get infinitely far on one edges, then, and so kind of filling in this outline is the content of the exercise, basically. It's a sum over n and m of these coefficients I'll denote by a and m times p to the n 1 minus p to the m, where a and m is the number of possible regions. So the number of possible C having exactly n oriented 1 edges connecting. Can everyone see down here still? Connecting elements of C and M edges greater than 1 with first endpoint in C. So these are the boundary edges kind of poking out. So you can show, and this is part of the exercise, that the sum over n for fixed m of A and M is bounded above by a constant times 9 to the M for a large constant. And then from that, you can use this formula to conclude that PC vector is less than or equal to 8/9. So yeah, try doing this exercise. Like I said, it's not prepared for the tutorial session, but it's nice. Okay. Okay, great. Yeah. I'll also say that this class MP, I think, again, maybe modulo some niceness conditions, should be the only time where you see flat pieces, except of course, if you take the definition of M, which I guess is gone, and you replace 1 by any other positive number, so you've really just scaled. And of course, you also will see flat pieces in this case. But this is really supposed to be the only time that this phenomenon happens. There's some, maybe I'll just quickly say there's been a little more work on measures in this class. So there's a theorem a little while ago by Baudevant and a couple other people, where they got kind of asymptotics for the passage time close to the axis for this class. So for all lambda between 0 and 1 on the event that the origin is on an infinite oriented path of 1 edges, we have the limit as n goes to infinity of the passage time from the origin to the point n times 1 minus p times lambda divided by n is 1 plus 1 minus p times 1 plus lambda squared over 2 plus some correction that's order 1 minus p squared. So this is like a parabolic correction off the cone. As far as I know, I think this is the best result in this direction. Okay, so yeah, as you can see, a lot of what I'm saying today is kind of a, collection of results about the shape and about some basic properties to kind of orient you towards the, the main things to expect in the model going forward. I have a little bit more to say about the shape. I call this section high D shape results. I'm going to erase the exercise so I don't have to break this, if that's okay. There's a little history that I don't think we really touched on in the first lecture, going back to Eden in the 50s, Murray Eden. So he introduced a model called the Eden model. It's slightly different from this, so apologies, but kind of morally, it's FPP with exponential weights. So this was kind of like first version of the model, and Eden and also Richardson looked at simulations of this growth model, and what they saw, as I remember, was kind of something that looked vaguely like a Euclidean ball, but it was kind of ambiguous. So I think it's fair to attribute to them the question of, is the limit shape for the Eden model a Euclidean ball? That would be, I think, kind of tantalizing, because it would indicate that perhaps aspects of the model aren't really sensitive to the lattice, which would probably make some things accessible that might otherwise not be accessible. But as far as I know, based on better simulations over time, and also the results I'm about to say, this is actually believed to be false for any dimension, at least 2. So the model really should feel the lattice in some sense. And there's work in high dimensions, really as you take D very large, you can explicitly estimate passage times on the axial and in diagonal directions to make bounds on the value of mu in these different directions. And these techniques have been used to answer this question in the negative, at least for D sufficiently large. So I'm going to credit this to a couple different people: Kesten, Coronet, and a couple other people, and also Bertrand and Ferdinand. The latter 2 proofs being computer assisted. They were able to show that if D, so the best result, as far as I know, is this Bertrand and Ferdinand, where they showed if D is bigger than 22, then B for the Eden model is not a Euclidean ball. And with kind of similar ideas, Dar and also the most recent version of the theorem I'll state is due to Alfinger and Tang, were able to really study the behavior of mu kind of for general distributions, general edge weight distributions F as D became large. So it's Alfinger and Tang. So the version of the theorem I'll state is due to Alfinger and Tang. The limit as D goes to infinity, so for fixed edge weight distribution F, but taking the lattice to have larger and larger dimension of mu in the E1 direction, and then we need to scale it appropriately as a function of D. It turns out the scaling, and this was already known by Dar, is log D over D. So if you rescale by D over log D, then you get 1 over 2a for an explicit a between 0 and infinity inclusive. So it's, after a moment's thought, it's kind of clear that the behavior of this, this mu should depend on what the distribution looks like near zero or near its infimum. Because as you get more and more paths, it becomes easier to take lower and lower weight edges. And so this A is related to the behavior of the distribution function f near zero. Okay. Yeah. Yeah, they're also able to show, maybe for some very broad class that you don't have a Euclidean ball as well. I don't think they get anything, as far as I know, they don't get anything quantitative about D, though. Yeah, that's a good point. No, but yeah, so it follows from comparing mu in the E1 direction to mu in a diagonal direction, really from like explicit estimation of passage times along paths. I think they have to do a second moment argument to say, you can find paths that have passage time on a certain, within a certain window. Yeah. Okay. Good. So let me talk a little bit about extensions of the shape theorem. I'll just talk about a couple possible extensions. There are others that I'm not going to cover here because I don't have an arbitrary amount of time. But one fact that's very interesting and was already noted by Cox and Durrett. So we saw in the statement of the shape theorem's proved under a moment assumption. And the moment assumption is actually a necessary and sufficient condition for the shape theorem. So if you don't have enough moments of your edge weights, then the shape theorem will break down. There will be some vertices out there that have kind of larger passage time than you would expect from the shape theorem. But even still, so even when the moment condition fails, something weaker is still true. So we still have a convergence of T0 nx rescaled by n to mu, where you have to define mu slightly differently if you don't have finite expectations, but some mu in probability. So you still have this kind of a weaker version of this kind of law of large numbers behavior, even if you don't have a lot of moments of your edge weights. Kind of morally, what's going on is this phenomenon that we already saw in the first lecture, that because you have a lot of paths to connect the origin to nx, there's kind of a mollification going on of the edge weights. The infimum operation is kind of pushing things down even when you don't have a lot of moments. And in fact, you can define a modified version of the passage time t, which I'll call t hat, such that the shape theorem in the strong sense, not just this kind of improbability convergence, but the strong sense stated in the last lecture holds or T hat with the above mu, and also T and T hat kind of don't differ by too much. So T minus T hat is a tight family. So the difference between T and T hat is kind of order 1 uniformly. So this idea, and versions of this idea have also come up, have been useful for proving other things in the model. So I think it's worth, just saying very briefly how this works. Let's just talk about the case D equals 2, because even the kind of combinatorial construction for higher dimensions gets pretty complicated. So if we choose some number m large, then the probability TE is less than or equal to m becomes arbitrarily close to 1. Not just greater than PC, but significantly greater than PC. And so by percolation arguments, really Bernoulli percolation arguments of a classical type, there exist infinitely many circuits around each vertex so where each edge E in the circuit has TE less than or equal to m. And also each circuit, each sufficiently large circuit anyway, intersects the unique infinite cluster of such M edges. So there's exactly one infinite connected component of vertices where every vertex is mutually reachable from every other vertex by a path of edges less than or equal to m. So the way this tau hat is defined we take the innermost such circuits Cx and Cy around vertices x and y. They're connected by an infinite path of m edges going into this infinite cluster. We simply define tau hat xy to be tau from Cx to Cy. So since the connection from Cx to Cy, every edge takes weight less than or equal to m, the passage time, so this passage time over here has all moments. So it's kind of clear because we expect that we don't have to look too far for these circuits, that the difference between passage times, the passage time t and the passage time t hat should not be too large. That's this tightness that I described over here. And then, as I said, because the connection between the circuits has not very large weight, and also because of properties of percolation, this path doesn't have to be very long in the Euclidean sense. this passage time is much more nicely behaved. So this really tells you that the kind of bad tail behavior of T is all coming from, trying to get to these circuits. And then once you get to the circuits, everything behaves kind of nicely. Yeah, around each of them. And you can see why, this gets a little more complicated in higher dimensions because you need to take the smallest hypersurface around each of them. Yeah, but morally, it's the same idea. Okay, good. So yeah, there are other versions of the shape theorem for IID weights than this. You can, for instance, introduce the possibility that some edges have infinite weight, and there are shape theorems that have been proved for this model as well. I won't really try to go into this in the interest of time, but I will talk about one other useful extension, which is to non-IID models. So instead of taking independent and identically distributed edge weights, we'll consider the case where the TEs just have some joint distribution that's translation ergodic. So this is obviously an extremely broad, class of models, and a lot of stuff that's believed about the IID model shouldn't be true at this level of generality, definitely. But at least a shape theorem is known. So the first shape theorem is due to Boivin in the 90s. So we showed a shape theorem in this generality, though he also needs the analogs of the moment condition from the Cox-Kesten shape theorem and this F0 less than PC assumption. So the analog of a moment condition that he takes is just a moment condition on the edge weights themselves. And the analog of F0 less than PC is really kind of implicit because I don't think there's such a good characterization of when you can have unbounded limit shape in this case. But okay, he proved a shape theorem, modulo these small technical points at this level of generality. As I said, a lot of stuff that's true or expected to be true for the IID model shouldn't be true at this level of generality. And there's a possibly surprising, I guess I don't really know what surprises everyone in the audience, so we can say question mark. But there's a surprising theorem of Hagström and Meister, who showed that to state informally for a second, all allowable, maybe just kind of basically all limit shapes are attainable modulo the stuff that's really forced on you by symmetry. So let me just state it formally. So suppose B is compact, convex, and satisfies the condition that whenever X is in B, also negative X is in B. Then there exists a translation ergodic distribution with the limit shape B. And the construction is actually explicit. So they give an explicit construction of the weight distribution corresponding to a given shape. There have been specific ergodic models that have been studied, both kind of ad hoc ones that have been invented to produce kind of degenerate behavior that you don't expect in the IID model, and also some ergodic distributions that arise kind of more, arguably more naturally, like when your edge weights are induced by an easing model. So you assign weights 0 and 1 depending on whether the edge is open in the FK representation of the easing model. So there's a lot of, there's a lot of room in this universe of translation, ergodic distributions. There's a lot of, stuff that should be possible. I think, there's still a lot to be done, especially in specific examples. Yeah.
In those models, for example, you don't need to have
No. So the way it's stated here, it is enforced that the distribution is invariant under the rotations. If you demand not just that it's translation ergodic, but also that it's invariant under rotations, then the limit shape will be invariant under rotations. I think their argument will still work in that case to produce rotation. It will produce any shape that you want with the additional condition that you're invariant under the rotations. No.
So does that mean the distribution in the vertical direction?
Well, yeah. So at the level that the theorem stated, it can be, because translation ergodicity, isn't going to force that. So, if you want to produce a limit shape that's not, symmetric with respect to the axes, what you're going to get by their construction is something that has different distributions in the two cases. Yeah. Oh. Yeah, that's a good point. Yeah. So the comment was that it was already observed that you have a limit shape in the ergodic models if the edge weights are bounded. That makes sense because to get the limits in direction, like rational directions, as in Riddhi's lecture, that's just the subadditive ergodic theorem. Boivin, like all the work he has to do is this maximal inequality, and that just is immediate, like in the IID case, if you have bounded weights. So yeah, that makes sense. Yeah. Yeah, it's from the fact that mu is a norm, and that's going to be an exercise from the tutorial, but that follows from the subadditivity of T. So the subadditivity in the limit becomes the subadditivity of the norm mu. Yeah, that's also a good point. Yeah, and that's really forced on you by subadditivity. All these things are really like mandated. Okay. So I'm definitely running slow. I've only got 5 minutes, so I will state one or two more things, and then I think a couple assumptions I had said I was going to get out there for other lectures. Maybe I won't have time to state, but I've gotten a lot of questions, which has been great. So thank you. So one I think interesting result that's been used a couple times like in a paper of Damron and Hockman to construct kind of interesting examples of limit shapes is this result due to Cox and Kesten instability of the limit shape. So I think it's actually due to Cox and Kesten and to Kesten. So it says that the limit shape is continuous under weak convergence of distributions of the edge weights. We're back in the IAD case now. So if Fn is a sequence of edge weight distributions, and Fn, the sequence Fn converges to some distribution F weakly, then if I denote the this shape norm in the case of Fn by mu n converges to mu. So there have been extensions of this as well, for instance, to the case I already mentioned where the edge weights can take value infinity. But I don't think there's anything quantitative known in this direction, which would be very interesting if someone could say something quantitative. Yeah. Really? Okay. 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 Yeah, okay, that's good. Yeah, thank you. Okay, so there is a quantitative version of this, at least in some cases. That's good. No, it's known for all directions. Yeah. Yeah. Okay. Okay. So I've only got what I guess about 7 minutes. Okay. So right. In the case, so in certain cases. It's known, it's known that you can make comparisons between the shape norms mu for different distributions. There's a theorem due to Vandenberg and Kesten. In the 90s, which says, so if, let me also actually cite it to Marshan because she studied the case where you have a percolation cone. So if F0 is less than PC, and if F is quote unquote more variable. I'll describe what this means in a second. This is some stochastic ordering. More variable than another distribution F tilde. then mu of E1 is less than mu tilde of E1. So in here, the E1 is actually important, or at least somewhat important, because if the two distributions are both percolation cone cases, then in the percolation cone direction, you don't have this strict inequality. So this more variable condition, so this is the condition that integral of phi df is less than or equal to, more variable, and also f is not equal to f tilde. So strictly more variable. More variable means integral phi df less than or equal to integral phi df tilde for all concave increasing functions phi. That's kind of, you have to sit down and unpack this condition a little bit, but it actually is kind of a natural condition for making this comparison. So there is a case where you can, compare the shape functionals. Kind of interestingly, it's a good exercise as well to find two distribution functions where one is more variable than the other, but they have the same mean. So you can push down the shape norm without changing the mean of your edge weights. Yeah. This is f is more variable than f tilde. Yeah. Yeah. Thank you. Okay. Right. I'm kind of debating whether I should open the next topic or just stop. I think I'm basically out of time. So why don't I have to apologize to the other speakers because I'm leaving a couple things unstated, but why don't I stop here and leave it to their courses. So thank you.